So tonight we're going to talk about the equilibrium constant. And this is what we use to quantify the concentrations of reactants and products at equilibrium. Remember, equilibrium is where the rate of the forward reaction is equal to the rate of the reverse reaction. It does not mean that the concentrations are equal. So if we look at our generic equation here, A and B reacting to form C and D, where the lowercase letters are the coefficients in the balanced chemical equation, we note that in brackets around A, that indicates molar concentration of A. So similar for B, C, and D, the brackets mean molar concentration. K, can you tell the difference in these two Ks? This is a non-italicized K, and this is italicized. So capital K, not in italics, is the abbreviation for Kelvin. Variables, when typed, are typically italicized, so they're a little bit slanty. So when it's slanty like this, that means it's the equilibrium constant. If you just kind of look at what you're doing, you should be able to tell them apart, but it's kind of unfortunate. So this is the formula for the equilibrium constant, and it's known as the law of mass action. And it's really not too hard to remember. Just like delta something is always the final minus initial, a lot of these things are the products over the reactants. So we do the products on the top, the reactants on the bottom. It's the concentration of the products, each raised to a power equal to their coefficient. So if it's a 1, you can write the 1 or not. If it's a 2, it'll be squared. 3, it'll be cubed, etc. And then in the denominator, we have the reactants. And of course, there could be more or fewer reactants or products, but that's the general form. So let's practice this. What is the correct expression for the equilibrium constant for this reaction? 2A plus B to form 3C. D, yep. Because we want the products, so there's only one, molar concentration of C raised to the third power, divided by A squared times B. Any questions? So we can apply the law of mass action to balanced chemical equations. We have an example here, N2O5 forming NO2 and O2. So again, concentration of the products. Here this one has a coefficient of 4, so it's raised to the fourth power. O2 is a 1. And down here, the concentration of the reactant squared. The coefficients become the exponents. Okay? So express the equilibrium constant for the combustion of propane as shown by this balanced chemical equation. So K equals, what goes on top? Yeah, we're doing the products, CO2, and what's the power? 3. And H2O to the fourth power, divided by C3H8 to the first power, and O2 to the fifth power. Okay. So that should seem like really friendly compared to kinetics, right? You know, we'd like to be able to do stuff like that for the rate law, but we can't. Remember, only elementary steps. So what is the significance of the equilibrium constant? When K is very large, that means that the concentration of the products is large and the concentrations of the reactants are small. That makes K a big number. Well, if the product concentrations are high, reactant concentrations are low, that tells us that the forward reaction is favored and that the equilibrium lies towards the product side. And what do we mean by big? Something like 1.9 times 10 to the 19th power. When we say big here, we mean big. Okay? Any questions about that? If K is very small, it's the opposite, right? That means that the product concentrations are very small, the reactant concentrations are very large. K is a small number. The reverse reaction is favored. There's going to be more reactants than products at equilibrium. And again, what do we mean by small? This one is 4.1 times 10 to the minus 31. Super, super small. It's important to note that the equilibrium constant says nothing about how fast the reaction gets to equilibrium. It could take 5 years. It could take 2 seconds. It doesn't say anything about that. It just says where it's eventually going to end up. So if K is very small, reverse reaction is favored. K is very big, the forward reaction is favored. And if K is approximately 1, then neither direction is really favored. The forward reaction, it just kind of goes about halfway. And that's about. So look at these pictures here. These are illustrating equilibrium mixtures of A, which is red, and B, which is black, at 3 different temperatures. And we have this reaction. A forms B. So at which temperature is the equilibrium constant the largest? C. A large equilibrium constant means the reaction goes far to the product side. So in this picture, we see a lot of the product, the black spheres, and very little of the reactant. This one has more product than either of those. Which of these has the smallest equilibrium constant? A. A would have the smallest because it's got the most reactant relative to product. Again, looking at an A to B, here we're told the equilibrium constant is 10. A reaction mixture initially contains concentration of A that's 1.1 molar and B that's 0 molar. Which statement is true at equilibrium? Would A be 1 molar and B be 0.1 molar? Or the opposite, A 0.1 molar and B 1 molar? Or equal concentrations of A and B? Yeah, it should be B. Because if we write the equilibrium expression here, K equals the concentration of B over the concentration of A. And we're told that that equals 10. So the concentration of B must be 10 times as large as the concentration of A. 10 is relatively close to 1. This is still fairly in the middle compared to those super duper extremes. So how you write the reaction makes a difference here. If you write the reverse reaction, the equilibrium constant can't be the same because now you made the products reactants and the reactants products. So just like when we did Hess's law and added chemical equations and multiplied by coefficient, you had to multiply delta H, etc. There's some rules like that for the equilibrium constant. But where delta H was a lot of multiplying or dividing or 1 over, here things are raised to powers, okay? So it's a little different. So let's look at this. Here we have an equation written in the forward direction and in the reverse direction. Let's write the equilibrium constant expressions for both of them. So for this one, we have c cubed over a times b squared. For this other one, we've got a times b squared divided by c cubed. The reverse reaction is the inverse of the forward reaction. Any questions? It's just upside down. If you multiply the coefficients by a factor, you raise the equilibrium constant to the same factor. So again, with made up alphabetical reactions, let's look at how that works. So this is the same equation. So c cubed over a times b squared. Over here, we're taking all of the coefficients and multiplying them by the same number, n. So then we've got c raised to the 3n power, a raised to the n power, and b raised to the 2n power. We can factor out that exponent and say that this, well, let's do it this way, that this k prime coefficient raised to the n power is equal to c cubed over a times b squared. And that is true whether you're multiplying by a whole number like 2 or by a fraction, like 1/2. If you're cutting it in half, then you're essentially taking the square root of the rate constant, not the rate constant, equilibrium constant.
Shouldn't all that be to the n? The c over a b squared?
Yes, I was sloppy. So this is equal to not k prime to the n, but k to the n. Yeah. So then k prime equals kn. Thanks for pointing that out. That was not right. Any questions? If you add chemical equations to get an overall equation, instead of adding the equilibrium constant expressions like we did with delta H, we're going to multiply them. So it's like you took the orders, or you took the operations and you cranked them up a notch, from adding to multiplying, from multiplying to raising to a power. So here, so if we add these two equations, what do we get? A plus 2b in equilibrium with 2b plus 3c. And so what does that simplify to? So to find the equilibrium constant for this guy, we're going to take those equilibrium constants and multiply them. We have b squared over a times c cubed over b squared. And the b squareds cancel out. So k equals c cubed over a, which is exactly what you get if you write it out from the equation. It's really some kind of cool math, but if you're not into that, it's just like this magic spell thing, right? Say the magic word and it works out. Okay, so the reaction A going to 2B has an equilibrium constant of 0.01. What's the equilibrium constant for the reaction B going to 1/2 A? So what has been done to the chemical equation? Yeah, oops. Yeah, so we reverse the reaction. So that means we invert K. And we multiply the coefficients by yes, 1/2. So multiplied by 1/2. So then what do we do with K? Raise it to the 1/2 power. So there's K is 0.01, so 1 over 0.01, and then the whole thing to the 1/2 power. Well, what is, I knew I forgot something. What is 1 over 0.01? 100. So this equals 100 to the 1/2 power. And what is something raised to the 1/2 power equivalent to? The square root. So what's the square root of 100? It's 10. Yeah. Any questions? Okay, let's practice manipulating an equilibrium constant to reflect changes in the chemical equation. So, consider the following chemical equation, and here's the equilibrium constant given to us at 25 degrees Celsius. We don't use the temperature in the calculation, but as with rate constants, equilibrium constants can change with temperature. So they are typically specified, the temperature. Calculate the equilibrium constant for this reaction, also at 25 degrees. Well, what's happened here? Yeah, we reversed the equation. And then what happened? We doubled it, right? Multiplied by 2. So K equals 2.2 times 10 to the 6. Inverting something you can do by making the exponent negative. So I could say this is raised to the negative 1. That's 1 over the rate constant. And then I also have to raise it to the 1/2 power. So I'll raise it to the negative 1/2 power. So kind of depends on how your calculator works. One way you can do this is to put parentheses around 2.2 times 10 to the minus 6, and then use that caret thing, or this one has x to the box, and put negative 0.5 up there.
Wouldn't it be -2?
It's raised to the negative 1/2 power. And my calculator's not appreciating that at all. So it's the square root of 2.2 times 10 to the minus 6. Well, 1 divided by 2.2 times 10 to the minus 6. $674. So this can be written different ways. 1.2 times 10 to the minus. It's 10 to the plus 6. It's 6.74 times 10 to the minus 4. So it's 10 to the minus 6. Yeah. So, in case you haven't noticed, we're dealing with exponents kind of a lot in this class, right? So, there are some pages in the appendix of your book that review things like logarithms and exponents. Yes?
Why is it to the minus 6?
Because it was, because I don't know what my head and my mouth are not communicating. I had done it with minus 6, and then I recognized that it was actually plus 6, and then I got confused and wrote the minus back in again. It's this guy up here. That was just really bad example here. That guy to the negative 1/2 power. Yeah, thanks for pointing that out.
So the 6.74 times 10 to the negative 4th, was that?
Mm-hmm. Yeah. Any questions? It wasn't supposed to be that hard. Okay, predict the equilibrium constant for the first reaction given the equilibrium constants for the second and third reactions. Could we combine the second and third reactions to give us the first reaction? Yeah, we can. So we're trying to get this guy, right? So I want CO2 as a reactant. This one has CO2 as a product, so I want to take this one and reverse it. And so the rate constant for that is going to be 1.0 times 10 to the 5 to the negative 1 power, or 1 over 1 times 10 to the 5. Up here I have methanol as a product. This one has methanol as a product. Let's add that one in there. Did I do anything to that equation? No. So what happens to its rate constant? Stays the same. So that's still 1.4 times 10 to the 7th. So when I add these two together, the COs cancel out. The 1 H2O here cancels 1 down there.
Isn't it H2,
Ah,
There we go.
not H2O?
Yeah.
yeah.
Plus 2H2. That's better.
You'd think I'd be able to, just copy something down. CO plus 2H2 makes CH3OH. There. Now this looks like that. Okay. So the COs cancel out, and the H2s add up. So on most apps, I can double tap my pencil and it turns into an eraser. And I finally really got used to that, and this app does not do that. And so I'm tapping and scribbling. It's just not so great. So when I add these two equations, what do I do to the rate constants? Multiply. Not like delta H. It's kind of the same idea, but we've taken it up a notch. Instead of adding, we're going to multiply. So this is going to be times, right? $140.
Yes.
I did it a different way, and it's still 140. Any questions? Yes.
For practical lab work notes, we have to, if we were gonna, try to discover the missing constant, would we have to make sure that both those other constants that we use were at the same temperature?
Yeah. Yeah, they'd have to be at the same temperature. Yep.